Can you believe that today is the last new lesson for Calculus BC? And I'm not here to share it with you. How crappy is that? That is crappy. But I'll be back and we can celebrate next class. Anyway, let's talk about calculus of vector valued functions, because doesn't that sound exciting for our last lesson? I can't wait. We are going to use these guys right here, so don't forget our special unit vectors. Remember, I is the horizontal unit vector and j is the vertical unit vector. So anyway, what is a vector valued function? Well, I'm glad you asked. A vector valued function is this right here. It's written like that. What does that mean? Well, f and g are real functions, and they're coefficients of I and j. So remember last class we looked at coefficients of I and j as constants, and then you have a vector. Well, now we have a vector valued function. We can also write it like this, just like we could before, where we just put the horizontal and vertical components inside these angle brackets. But there's other notations too. So still, what does this mean? Let's take a look at an example. The graph of a vector valued function is the curve that's traced out by the terminal points of the position vectors. So again, what does that mean? Let's take a look at a real example. So here is a vector valued function. You can see the coefficients of I and j, instead of being constants, they are functions. And so all we do is we just pick values of t, plug them in, and just see what we get. And you're going to find this actually acts a lot like parametric equations. In fact, that's why they're put together in the same unit. So let's just make a table of values. And if we let t take on, for example, these values, we get these values of a vector. Let's just do a couple of them so we can see exactly where these are coming from. If we let t equal 0, cosine of 0 is 1, sine of 0 is 0. So you'll have 1 times I plus 0 times j, which is 1, 0, just I. If we let t equal pi over 4, cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is also root 2 over 2. So I can write it like this in its component form, or I could have said root 2 over 2i plus root 2 over 2j. Either way. If we just look at pi, the very last one, cosine of pi is -1, sine of pi is 0, -1 times I plus 0 times j would be -I, or the vector -1, 0. So now if I plot these vectors, so for instance, this one that's highlighted purple, starting at the origin, go horizontally 1 unit, there's my terminal point right there. The yellow vector, root 2 over 2, root 2 over 2, and root 2 over 2 is about 0.7. Starting at the origin, if I go over root 2, over root 2 over 2, up root 2 over 2, there's my terminal point right there. The green one, starting at the origin, I'm just going to go up 1 unit vertically. There's my terminal point. Blue, starting at the origin, negative root 2 over 2, positive root 2 over 2. There's my terminal point. And then finally, -1, 0. There's my terminal point. If I kept going, I would trace out the whole entire circle. Now it's the pink part specifically that is the graph of the vector valued functions. These vectors here are just to show you where the points are coming from, but it's the terminal points that make up the actual curve. So you can see it's actually the same curve as the parametric equations cosine t sine t would make. Coincidence? Not at all. It works exactly like parametric equations. Okay, let's take a look, see what we can do with this. Let's look in some calculus. And guess what? we can do limits, derivatives, and integrals of these bad boys, and it's no different than the limits, derivatives, and integrals you've done before. You just get to do it twice, because doing it once wasn't fun enough. If you want to take the limit of this vector, then just do the limit of the horizontal component and the vertical component. And again, they're vector valued functions because the components themselves are real valued functions. Which is take the limit of the horizontal, limit of the vertical. The vertical we can do L'Hopital's rule on, and you get your answer. And there is the limit. The limit of this vector valued function would approach this, this vector. If we wanted to take the derivative of a vector, just take the derivative of the components. So the derivative of the horizontal component would be -1. The derivative of the vertical component, 4, and then remember that's t to the 1/2. Multiply by the exponent, decrease the exponent by 1. You could write your answer like this. You could write your answer like this. Either one. Doesn't matter. Easy peasy. Even integration is straightforward. It's as straightforward as the integration is. And you guys know, sometimes integration is straightforward and sometimes it isn't. Just depends. But you just get to do it twice. Now it also becomes a little messy. So I recommend splitting it and just do the two integrals separately. Unless it's like really, really easy and it's like one step you can do in your head kind of thing. But we have a horizontal and a vertical real valued functions for the horizontal and vertical component. So for the horizontal, just take the limit of the horizontal. For the vertical, I'm sorry, not limit, integral of the horizontal. And then for the vertical, you can take the integral of the vertical. And again, it's as straightforward as they are. This one right here, you could do u sub. The derivative of the inside, it would be -2t, and you have the t, you just don't have -2. You don't have a constant multiplying by constant. That's a dead giveaway that u sub is definitely going to work. But it's also a dead giveaway that you can do the shortcut if you got the hang of it. Remember, the derivative of this would be -2t. We have the t, but not the -2. So let me multiply by -2, but then I have to divide by a -2. And so now I do have the derivative of the inside, and I can just integrate the outside. The the integral of e to a power is just e to that power. And then you can check it going backwards that it works. Just plug in your limits, and there you go. There is your vertical component for the antiderivative, or for the antiderivative evaluated at limits. If we do the vertical one, again, the derivative of the inside is there. So I could have done the shortcut because I could have multiplied by 2 and divided by 2. But I decided to also show you u sub to remind you about that. So either way, but notice the 1/2 showed up right there with u sub. No coincidence. But anyway, if you do u sub, you let u equal the inside. Just don't forget also to change your limits of integration. But then you wind up with this. And whether you use the shortcut or not, you're going to wind up with this. And the way to integrate a natural log, you could, if you remembered, if you remember the formula, which honestly I never do, it's a pretty easy, quick integration by parts one. And so I just always do integration by parts. Just doesn't come up often enough for me to remember it. But there is a formula, and if you know it, you can go ahead and use it. But anyway, I didn't. So integration by parts is right here. I did u sub up above. So instead of doing u sub, I did integration by parts with u and v. I did v and w, and here's the formula. I changed it to this, and I'm using w and v. But anyway, just doing integration by parts, and I get down here. So there is my answer. There's two more examples. The next one is weird. The last example is pretty straightforward. It's another one of those. It's what you've done before in the past. You just do it twice. But this next one is weird. So vector parameterization of a tangent line to a curve at t equals t naught at some given t. What does this mean, vector parameterization? I mean, it says right here that it is this where the tangent vector r prime of t naught is a direction vector for the tangent line. I mean, it's a bunch of words, but what does it mean? So the next example is going to show it. It's not going to be obvious at first, but by the end of the example, hopefully it will make sense what a vector parameterization of a tangent line to a curve. So let's take a look. Let's look at this vector valued function. It's the same one we did at the very beginning. It's the one that made this circle. So plot this this vector valued function, already done. It's the green circle. Together with the tangent vectors at t equals pi over 4 and t equals 3 pi over 2. Let's just do that first part. So tangent vectors, all you do is you find the derivative, and again, just take the derivative of the components, which are right here, and then plug in the point. So we're plugging in t equals pi over 4. Negative sine of pi over 4 is negative root 2 over 2. Cosine of pi over 4 is positive root 2 over 2. So this is the tangent vector for r at pi over 4. So if we take a look, now remember vectors, when you're plotting them, we looked at last class, you can start plotting the vector anywhere. It doesn't have to be at the origin. It doesn't have to be at a specific point. When we're talking about tangent vectors, it makes sense for the initial point of the vector to be that point of tangency. So at pi over 4, the terminal point for r would be right here. And starting here and then going negative root 2 over 2, positive root 2 over 2. So starting right here, negative root 2 over 2, positive root 2 over 2 puts our terminal point right there. There is our tangent vector. And just like it's set up here, the tangent vector is a direction vector for the tangent line. So right there, you can see it's, if I drew an actual tangent line, it goes right through that vector. If we did the same thing for t equals 3 pi over 2, again, plugging 3 pi over 2 into negative sine t and cosine t, we get the points 1, 0. So starting at the point on the curve, it'd be right here, and then we just go 1 unit in the horizontal direction, and there's my tangent vector at theta equals, at t equals 3 pi over 2. So there's my tangent vectors. Now let's look at this part. Find the parameterization of the tangent line at t equals pi over 4, and then find the equation of the tangent line in rectangular form. So find the parameterization of the tangent line at t equals pi over 4. We've actually looked at that. We've looked at making a parameterization for a line. We could have found the equation of the line in rectangular form and then written a set of parametric equations for that tangent line. But we also know that there's a whole bunch of different options for what the horizontal and vertical parameter are, or for oh my gosh, I can't speak. We've looked at when we did parametric equations, there's no one answer. There's a bunch of different parametric equations that can describe the same curve. So I'm going to show you one of them. Now there's a whole bunch of other stuff kind of behind the scenes, more meaning to this. I find it kind of weird that this is in BC the way it is when we don't get into more meat of it. But just chalk it up to, it's one of those things in math. You learn about it, You'll learn about the applications and the other stuff like when you get into more engineering math. But anyway, find the parameterization of the tangent line. We're going to find the parametric equations for the tangent line. That's really all that means. So this was the formula that I gave you up in the bubble. So r at that point, remember we're talking pi over 4. So if, remember here's our r, if we let t equal pi over 4, then we're going to get root 2 over 2, root 2 over 2, which is what this is. So this right here gave us that. We found r prime at pi over 4. So that is this. And then the t is just the coefficient here. And you can kind of see this is like m slope derivative x plus b, your initial point. It's where the equation is kind of coming from. So now if we put this all together, if I distributed the t to these two coordinates and then added my vertical components, or sorry, horizontal components together, you get root 2 over 2 plus a negative root 2 over 2t right here. And the vertical components, you get root 2 over 2 plus t times root 2 over 2, which is right there. And this is your parameterization, your vector parameterization for the tangent line. Kind of weird, but that's what it is. If we were to do the same kind of thing we did way back in the beginning, when we made a table of values and we found a bunch of vectors and we plotted the terminal points, in this case they made a circle. Well, in this case, if we did the same thing, it would make a line. Not just any line, it would make this tangent line. Now, let's also look, it says, then find the equation of the tangent line in rectangular form. Now, we can do this one of two ways. I'm going to do it the more complicated way because I do want you to see. Here is that vector parameterization that we just found above. Now, just think of this as a set of parametric equations because that's exactly what it is. We're going to rewrite in rectangular form just like we did when we covered vector parameterizations. We can solve the horizontal component for t and then plug into the vertical component. Or we could do it the other way, but I'm going to do it this way. So let's look at the horizontal component, which is right here. I'm just going to say x equals that because it does. It's the horizontal component. If we take this thing and solve for t, we're going to get this. Now, let me take the vertical component, y equals this thing right there. And I'm going to replace t with what it equals right there. Now I have an equation in terms of x and y, and if I just clean this thing up, distribute the root 2 over 2 across here, and combine any like terms that I've got, these guys combine to give me just one root 2, then I get root 2 minus x. And you can see that is a very nice equation of a line. And it's an equation that will intercept the y-axis at root 2, which is about 1.4, and has a slope of -1. And if you take a look at the curve at the tangent vector, then this point right here, if my graph was drawn accurately, this point right here would be hitting the y-axis at root 2, and it has a slope of -1. So a vector parameterization, this right here is just a set of parametric equations that represent the tangent line. That's it. That's all it is. So, I mean, yes, does it seem more complicated than just doing our old-fashioned what we used to do? Yeah, but it's more than I want to get into. But there are reasons for wanting to do this, because we can get information from the vector parameterization, thinking about what vectors tell us about magnitude and direction, and what we've done in parametric equations and speed and stuff like that. So there is a meaning behind this that we can't get from this, but for our purposes, it's all we have to do. We just have to know that this makes a line and it doesn't make any line. It's parametric equations that represent the tangent line. Noodle on that if you need to pause the video. We're going to do one more example. So, last example, the path of a particle satisfies this. Find the particle's location and velocity at t equals 4 if r of 0 equals the vector for 1. So, what does this mean? Well, this is the derivative, and it says the path of a particle satisfies this. We want to find the particle's location and velocity at this, at t equals 4 of this. So the location vector, this is the derivative of the position over time. So think of this as velocity vector. This is our location vector then. So we just have to integrate both parts. Integrate this, integrate this. And I didn't bother breaking this up. This is what I was talking about above. This is easy enough to do in my head. I don't need to break it up. But notice each one of them gets their own C. Integrating the horizontal component gets a C. Integrating the vertical component gets a C. And these C's don't have to be the same, so they get different subscripts. And yes, you have to write the subscripts. But now we can use this location vector at 0 to find C1 and C2, just like we normally did. Like I said, it's what we've done in the past. We're just doing it twice. So looking at the horizontal component, the value is 4 when t is 0. So let t equal 0. And then you can solve for C1. And then the vertical component, the value is 1 when t is 0. So let t equal 0 and you get C2. So now we know the location vector is this. And they wanted specifically the particle's location. Whoops. The particle's location and velocity at t equals 4. So here's the location vector. Now I'm just plugging in 4. And then we take the velocity vector, which they actually already gave us, and plug in t equals 4, and we get that. And then that's it. That's the end. That's it. There's no more. We've done everything. You guys can take the test. You know what? I'm going to call College Board and I'm going to say you guys are ready. We're just going to do the AP exam tomorrow. You'll be fine. It's great. We'll get it over with. Won't that be nice? You go to spring break. You don't have to worry about anything. If only we could do that. All right. Anyway, that's it. So good luck, and I will see you when I get back. Bye.